So examples, you can talk about paddy production in each year of a region. We can talk about price of a particular product. I can talk about closing price of a particular share. I can talk about rainfall in each day in a particular region. I can talk about number of international air passengers on each month. Okay, so we have, I mean, you can think of time series in every aspect of life actually. So some point I should mention here, see, for example, if I take that rainfall I have written in each day, and also I have written in particular region. So when I am talking about some time series, I have to specify those things clearly. For example, I can also talk about total rainfall in a month in a particular region. For example, total rainfall in a month in the northeast states of India. Or I can talk about total rain in a month in Rajasthan. Or I can talk about total rain in each day in Tamil Nadu. So I have to specify when I am talking about time series or some data, I have to specify those things properly. Otherwise, that does not make much sense to us. Okay? So these are something we should keep in mind, that in which time scale I am seeing the data. Is it a daily data? Is it a monthly data? Is it a quarterly data, or is it a yearly data? Okay, those things I have to keep in mind. Also, I have to specify that if there is some special things are there, I have to specify for what region I am talking about. And this is very, very important because, for example, if you compare the rain pattern in Tamil Nadu and maybe in Rajasthan, they are completely different. Or Tamil Nadu maybe in Delhi, they are completely different. In Delhi, we have rain mainly in monsoon session, but in the Tamil Nadu, we have rain in two sessions. That we have rain in monsoon, we have rain in December and January. Okay, so those things we should mention properly whenever we are talking about that. We should have clear idea about those things. Okay, now go back to previous slide. So a few points I just mentioned here. Okay, first point I have already mentioned that it is basically measured chronologically, that is measured with respect to time. Next point is basically that most of the cases the time series are modeled using stochastic process. Because stochastic process is basically collection of random variable where the collection is made with respect to time. So time series is basically modeled using the stochastic process. And the standard notation that I'm going to use throughout the talk is that I'll use this xt notation, and this xt stands for the value of the time series at the time t. Okay, so if I write x1, so x1 is the value of the time series at the time 1, x2 value of the time series at the time 2, and so on and so forth. That's what basically I am going to use. And then next two points are basically I have already discussed this. The time series analysis is very, very important in practice because time series arises in almost all forms of research, practical use everywhere. And then nowadays time series has, the tools of the time series are quite developed. So this is a powerful technique to do this. As Polash has already mentioned in one of the examples, that prediction is very, very important, especially that Orin example, because a lot of money matters. In case of the time series also, those forecasting is very, very important, because so you take a very, very simple example, very, very simple generic example. Suppose I am talking about demand of a product. Okay. Now, if I do not forecast it properly, and if we basically overestimate the demand, then there is a problem, because I may acquire more products, and if the products are perishable products, then it will actually next day I cannot able to sell them. So then there is a waste. And in case of the food chain, that is especially that raw food chain, that is a very, very important thing we should look into. On the other hand, if I underestimate the demand for future, for tomorrow or day after tomorrow, then I will acquire less amount of food, And so some of my customer may go empty-handed and they will go to my other shops. So in the market, my position will going to lose. Okay. So forecasting, time series forecasting in different font is very important thing, and we should do those things properly so that we should not incur any loss. The loss can be in terms of money, loss can be in terms of man-hour, loss can be in terms of anything. Okay, so before going into the time series, I hope Polash has already pointed it out that in statistics or in data science, if when I have a univariate data, I generally what we do is that we plot the data and try to see how the data look like. And from this visual inspection, we try to find out, is there any pattern? If I can find out any pattern visually, can we model that pattern? Can we take a model or can we formulate a mathematical model so that that pattern is captured there? For example, in this case, you see there is a very, very easily seen that there is an increasing pattern in the data. There are two things actually here. One is not only it is an increasing one, suppose I feed the linear model to the data. The linear model will look like that. Okay. If I suppose y is my data, I feed the data y equals to a plus bt plus epsilon. Okay. Polash has already talked about this kind of linear model. If I feed the linear model, their model should look like that one, this straight line. And from here, some points are very clear from the data. The data is basically, it is an increasing trend is there. Another point is very important here that almost after the same amount of time I have this lower points, and similarly almost in the same amount of after same amount of time I have that peaks. Okay, these lower points and peaks are almost equidistant. Another point we can easily see in this case that the spread with respect to the linear straight line, that spread here is much smaller than the spread here. Okay, so spread is also increasing. So those things actually, once I plot the data, we can see those things very easily in most of the cases. How we can plot this data, that I am coming. But first point that we want to do is that plot the data. Okay, I plot some data. What data this one? Those portions I will come one by one, but let us see some of the plots first. The next plot look like little different, not much different. Only change here is that maybe the spread are almost same in the beginning or at the end. Okay, maybe the spread are almost same in the beginning and the end, but still we have an increasing pattern. And let us go to the third plot. Here the plot actually completely changed. Maybe my regression line may be something like that. And in this case, regression line is almost a constant one. Constant in that basically I mean that it is parallel to time axis, and spread is also roughly same in the beginning to end through end. Okay, so we have actually basically seen three graphs there. In the first graph, there are basically increasing trend. I have peaks almost in the same distance, and then I have basically the spread is also changing. In the next graph, only change to the previous one is the spread is almost constant in this case, but still it is an increasing trend. The peaks are having equidistance, the time distance, and similarly the lower points are. And the third one is kindly haphazard, and here the trend is basically, the mean is basically not changing. The linear line, it is basically mean, linear line is basically mean, and it is not changing much with respect to time. And spreads and all those things are almost same throughout the data. Okay, so all those kind of data we can see in practice, and we may need to analyze this data. Of course, in this case, I have only talked about the increasing trend, but of course, in some time series data, I may have the pattern maybe like this. Okay, or in some time series data, maybe pattern maybe not linear even like this. Okay, so this kind of thing can happen. So those things I have not put here, but yeah, those things can happen. Okay, now there is one very important concept. Of course, this is theoretical concept, but it has much practical meaning. Okay, at the point I stop and I ask that if there is any feedback, I mean any question, anything, or I hope that you are able to understand, right? Okay, no comments, so I hope that everything is fine. So let us now talk about the stationary time series. So stationary time series, as I mentioned, it is a theoretical concept, but it has a very nice practical use also. And what is the meaning of the stationary time series? What is the meaning of the word stationary? Stationary means something which is not moving, which is fixed. Okay. So stationary time series basically means that it is not moving. It is not moving, but of course the value will have some up and down. But it is not moving. That basically means that on an average, the property of the time series is not changing. Okay. Let us go back to the graphs once again. Say here, on an average, the property is changing. What is changing? The mean is changing. If you see the mean of this part of time series, that is much lower compared to the mean of this part of time series. Okay, so mean is changing. That says that mean is changing with time. Not only that, in this case, variance is also changing. So if I see the variance of the data point in this part, that is much smaller compared to the variance of the data point in this part, because I have more spread here. I have less spread here. So here clearly the properties, that mean, variance, all those properties of the time series changes with time. You can see in the next plot, of course, variance most likely is not changing. The variance here and the variance here may be same, almost same, may not be exactly same, but very close to one another. But the mean is clearly changing. The mean here is much higher compared to mean in the lower part. Okay, so again the property are changing. But if you go to this one, that these properties are at least fixed. That mean is on average same, it is not changing that much. Variance spread is also almost equal, so variance is not changing that much. So this kind of time series we generally call stationary time series. Okay, so this is the intuition behind the stationary time series. So in case of the stationary time series, I have to check this whether basically these 3 points are true or not, that whether the mean is constant or not. That means mean should not change with respect to time. This constant with respect to time. Whether variance is constant or not, it is again with respect to time. And finally, whether the covariance or correlation between xt and xt plus s depends on this s or not. So what is this s? This is my xt, and here I have xt plus s. So s is basically nothing but the time gap between these 2 points. So the covariance or correlation should depend on the time gap only. This is called lag generally. So correlation or covariance between xt and xt plus s depend on s only, and s is generally called the lag. And that correlation should not depend on t, which is basically the time. So that means that whether I am seeing the covariance between these two, or whether I am seeing the covariance between maybe xt1 t1 and xt1 plus s, that should be same, because both the cases I take the lag to be same, which is same as s. Okay, so these 3 points we have to check if a time series is a stationary or not. Okay, so now of course let us see some these points I have already mentioned that well. This is a stationary time series because mean, variance are not changing. Also the correlation are not changing, but in this case you see that there is a clear change in the variance level. Okay, there is a clear change in the variance level. Similarly, well, well, I feel one of them I have not given here. So, okay. And this one is also interesting. See, this one, the main change is that in this case, in this part, the waves have more length. The waves length are high, and same is true in this part. But in the middle part, the length of the waves are very small. So what does this basically mean? This means if I find out the covariance between this point and this point, this will be high compared to covariance here. And so in this case, basically the covariance is changed. Okay. So these things are basically some visual inspection of the stationarity. If this kind of things happens after plot, that is not a stationary time series. The series should be something like this. Okay. Something like that. That mean is not changing, variance is not changing, waves are almost equidistant. Not that much of change should be there. I mean, some are very big, some are very small. This type of thing should not be there. Okay. So this is basically visual inspection for stationarity. There is statistical test also. I am not going into the exact test, but what I am basically going to tell you is that the test is called Decaf-Fuller test, and there the hypothesis, the null hypothesis we took as time series is not stationary, and the alternate hypothesis is basically different based on what I want to test with respect to time, in the time series. Okay, so in our case we try to test whether the time series is stationary or not. So we will take this is as a alternative hypothesis. So if the null hypothesis is accepted, we basically conclude that the data is not, that the time series is not stationary. If the alternative hypothesis is accepted, we induce or infer that the time series is a stationary time series. Okay, and in most of the cases in the time series analysis, we have to do both the things together. We have to do the visual inspection as well as we have to do the statistical test. Of course, there are several other tests for stationarity, but this one is a very, very popular test. So that's why I put it here. Again, as I mentioned, that exact test I am not going into, but as we will show that in R, we will be able to do this test very easily, and R also provide us the p-value for the test. So based on the p-value, we can reject or accept the null hypothesis. Okay. So basically, as we already mentioned that, well, the stationarity is an important concept. Why important? I am going to answer this question. But and to check if a time series is stationary or not, we basically do both kind of testing, that whether it is visual inspection we will do, then we will go for statistical inspection, statistical test. Okay. So after that, now the question is that, as I mentioned only the fact that, well, stationarity is an important concept. Now the question is that why this is important. The main reason of this one, the intuition behind this one is that, say, if I have a non-stationary time series, that means the property of the time series is changing. So in those cases, it is very difficult to predict the future if I do not model it properly. Okay. But in case of the stationarity, because the property is not changing, the time series on an average is not changing too much, so the prediction or forecasting are comparatively easier. So, and most of the model, as we see, models are basically based on stationarity. Okay. So when we try to do the analysis of some time series, what first aim will be to do some kind of operation on the time series so that we have a stationary time series. And there are several ways of doing this one. Some popular method for doing this one is basically nothing but doing differentiation or doing detrending. And that's what exactly I did for this time series. So I start with this time series, and I have already mentioned that in this case, this time series from the very basic visual inspection, it is clear this is not a stationary time series. So what I did, I take the log of this time series, which actually resulted to this one, and that actually, the spread now comes almost equal throughout the time series, taking log, but still I have a increasing trend here. So I detrend it. That means in this case, basically trend is a linear trend. It is basically y equals to again a plus bt form. So I estimate this a, I estimate this b. Then finally from yt we can subtract a hat minus b hat t. And this time series, if I call this is a new time series zt, that zt is basically plotted here. Okay. Zt is basically plotted in the next plot. This one. So then actually this trend is also gone. So this is a detrending process. Okay. So detrending can be done in this way also, and in some cases we can able to do detrending using differentiation also. So differentiation is basically nothing but that I start with the time series xt, and with some specific lag I divide, I subtract, like maybe if I take d equals to 1, I may write xt equals to xt minus 1 this way. So basically if I have the time series x1, x2, x3, so on and so forth, one value will be gone. The next point will be x2 minus x1, and then x3 minus x2, and so on and so forth. This is the differentiation of lag 1. Okay, differentiation of lag 1. Similarly, I can talk about any general d, and that d which lag differentiation I should take, that we need to think about. Okay, so this way, these are some popular methods to do the detrending. So first we plot, we check that if there is any trend, any seasonality, any change of the variance is there or not. So I have to do the transformation, and that, as I mentioned, for stabilizing the variance, the popular transformation is taking the log. So first take log if there is a change in variation. If then the variance is stabilized, maybe you can check for if there is a trend or not. If there is a trend, you may fit a linear regression with respect to time, and then you may subtract that trend, or you may do the differentiation of appropriate order. And then you have finally, when you have this kind of plot, well, we are satisfied, at least visually, this data look like, this time series look like a stationary time series. Then maybe we can do the statistical test also, and we basically, this statistical test will one extra layer of support to the fact that it is a stationary time series. This, of course, that depends on the result of the this test. Okay. So again I stop, and then I ask if there is anything to any question, anything.
Sir, there is one question.
Yes.
Sir, if there is a trend in the data, and if we are making it stationary, then how will we be able to capture the trend? Then the forecast may be wrong.
Of course, but that is not true, because again, let me answer from this one. Good question, very good question. Let me answer this one. See, when I have already mentioned, when you are detrending, you are basically finding out this linear. This is one way, finding out this linear regression, right?
Yes.
Okay. Yes. Now you see that suppose I have predicted some way I have predicted maybe future the point may be come here at some time point. Here the point may come here. So this is the point with respect to this stationary time series. Now to go back to original time series yt, so maybe I call this stationary time series as zt. So this is the forecast for zt. Maybe zt equals to some point, maybe 100. Maybe this is up to 1960. Maybe I take 12000. Okay. So this is basically the forecast for the stationary time series. Now to find out this one, I know that this should be nothing but Z 2000 plus A hat plus B hat into 2000. So I finally go back to my original time series. Clear?
Yes, thank
So
you.
this is the stepwise process. I first go to the stationary one, I model there, then I again go back because all the previous step I have done. So then I will go back to previous steps to have the estimate or forecast of the final time. This is basically the idea here. Hope that this answers your question. Yeah, nice question, good question. I should have mentioned that. Any other question? Okay, so I hope no. So let me proceed. Okay, now I will talk about the second part of this talk, which is basically exploring of the time series. So you have now I start with the data. Basically now I start with the data, and when I have a data, first thing will be to see how their data look like. Okay, explore my data, plot the data, and see how their data look. Okay, so this data I am basically going to talk about now. It is basically a air passenger data. It is a data in R. So we can use this data. I will show the data how it looks like. Before that, just let me tell what is the data about. So this data I will take. It is an inbuilt data in R. So I'll take it from R. And then the data actually consists of total number of international air passengers. Okay, monthly total number of international air passengers. So and the time span is basically January 1949 to December 1960. So let us first see the data. So this is basically that R Studio. I hope you know the R Studio, right? Is anybody there who do not have any idea about R or R Studio? Okay, so I hope that all of you have the idea of R and R Studio. So just what I have done is that as I told that I will use this data, which is basically air passenger data, and I first need to import the data into my work frame. So I just run the first line, that data air passenger, and that you can do two ways. Either click on run. You first keep your cursor on the line, click on run, or you just keep the cursor on the line and press Control Enter. So I did that, and now let us see how this data look like. I hope that all of you able to see the data. The data is here. So in the January 1949, there are 112 international air passengers. In the month February of the year 1949, there are 118 air passengers, and so on and so forth is go. Okay, and finally we have data up to the month of December for the year 1960, and the number of international air passengers were 432. Okay, so this is the data. So as I mentioned, first thing we will do is to plot the data. Okay, so let us first plot the data and see how it looks like. So when I plot the data, basically it comes here, and this is the data basically I have shown in the very first plot. Okay, so this data look like that, and as I have already mentioned those points, well, I have a kind of increasing trend. I have so increasing trend and mean is increasing. I have some seasonality here, and also I have variances increase. Okay, and the seasonality, if you look into the data, you will see that in general the value of the month July is higher. Okay, in a particular year, value in the month July, August, they are more compared to the values in the month of maybe January and February and December. Okay, so that's why this kind of pattern is coming. This is basically, these peaks are basically correspond to the months of July, August, June, July, August, whereas these drifts are basically corresponding to the month of December, January, and February. Okay, so this data looks like that. Now some point I should mention here regarding that R. In R, the time series are basically taken care with the help of some object which is called ETS object. And in this case, if you see the line number 8 here, if I execute it, it actually tells that this class function actually tells that what kind of object the argument is. And it is saying that is a time series object. In short, it is a TS. Okay. You can see several things here that what is the start point. Starting point is basically 1949, year 1949, and month is 1. You can see what is the end point. That is basically 1960 and 12. That is not very important for this kind of data where the data size is not that much. But if you have a very big data, then this kind of things are very helpful because then you cannot print the complete data on the console. So that's why basically in those cases, this kind of start, end are very, very important. We can see the frequency here. Frequency is basically nothing but in a particular year, how many times I have the reading. Okay, so it is a monthly data, so the frequency is 12. But if I have a quarterly data, frequency is 4. If I have a weekly data, the frequency is 52. If I have a daily data, the frequency is 365. Okay, so all those things we can do with some command. And then, as I mentioned, I can go now for the plot. So that plot I have, and with that I just draw the linear model. Okay, with that I just draw the linear model, and you know this one, that this one you have already seen. So in this case, what we have done is basically this is the data I try to model. This is the Y, and I model it with respect to time t, and I just use ln. Okay, that's what you have already seen in your Polash has already told you. So that line I fit, and that's what basically I have drawn in freehand also. So it clearly says that I have an increasing trend. I can talk about what box plot also, and it is basically based on the year. In the first year, the box plot like that, and so on. Sorry, it is basically the month. So basically, this is the box plot plot for this column, for January column. Then this one is the box plot for the February column, and so on and so forth. And this one gives us the clear idea that in the month 7 and the month 8, that is July and August, we have more passengers. Okay, we have more passengers, whereas in February or in 11, that is November, I have much less passengers. Okay, on an average, much less passengers. So this kind of exploration we generally do to understand what kind of pattern we have in the data. Okay, so so this is that. Okay, now again let us go back to our main plot. This plot. So this plot, as I mentioned, we have some variability in variance. Variance is increasing. So now what I am going to do, I am going to take log. Okay, I am going to take log, and I just save this after taking the log to the time series. I save this one into T air passenger, where basically this T transform time series. Okay, T transform time series. I just save it here. Now I just plot this data with a corresponding linear regression. Okay, so in this case, you see that the linear regression is done with the transform data, with the log data. So when we do this one, you see that now pattern changes. In this case, here the up and downs are quite close to the mean line, that is the regression line, but here it was far away from the mean line. But when I take the log, that is stabilized, that the distance, the spread here and spread here are almost same. Okay, so but still now I have the increasing trend. How I can reduce this increasing trend? Because in this case the trend is linear. If you have a linear trend, if you take the difference of the first order, I am done. Okay, so over this log data, I now take the difference and I save the data once again into the T. Once again into the T air passenger ticket.
Excuse me, sir.
Then I plot it. Yes, any question?
Yes, sorry to interrupt, sir. Sir,
No,
is
yeah,
it okay if the codes can be pasted in the chat box so that simultaneously we can run with our and we can check?
Right, but I do not want it that much now because you have a hand-on session.
Okay.
So those things you can try this in the hand-on session. I will definitely share the codes before that. Now just try to understand that what is happening.
Okay.
Okay.
Sir. Okay.
And I will, with the help of host Dr. Professor Saidam, I will share the slide as well as codes. Okay.
Thank you. Thank you.
Okay. So now, okay. So we are talking about taking log first and then taking the differentiation. And then when I plot that data, it basically turns out to be this way. And now if I add the regression line here, the regression line is something constant and the spreads are also not that much. And roughly that the wavelengths are also roughly not changing too much. Okay. So that's why visual inspection now tells us, well, this one is a stationary time. Of course, keep in mind, as some of you have already questioned, see, now what I'm going to do, I am going to model this time series, this stationary time series. But when you have to basically predict or forecast the original time series, after predicting this time series, you have to go back. Okay, you have to go back. So first you have to do the opposite inverse transformation of the differentiation, and then you have to do the inverse transformation of the log. Okay, and inverse transformation of the differentiation is not a problem because differentiation is nothing but, as I mentioned, it is xt minus xt minus xt minus d. So you just find out both the values, you just go back, and then the inverse transform of the log is basically nothing but e to the power. So those things we will do, and we will go back to the original time. Okay.
Excuse
okay.
me.
Now, yes, please.
Sir, can we take a direct differencing without taking log?
That may be a problem because differentiation does not stabilize the variance. Okay. Again, see, I am talking about very basic. This only sometimes the differentiation do not actually detrend also. Whether differentiation will detrend or not, that depends on what kind of trend you have. In this case, we have a linear trend. That's why one differentiation actually detrends. But suppose you have a quadratic trend, then you have to take two differentiations. So these kind of things are there. But for this preliminary course, keep this thing in basic. If I have a linear trend, one differentiation will do, but that I should take after log because I have taken the log to stabilize the variance. As I mentioned, in this case, variance is changing. That taking log actually stabilize the variance. Now I am detrending taking the differentiation. Okay?
Thank you.
Clear? Okay. Now it looks like visual inspection tells that it looks like we have a stationary data. Now we will go for some statistical test. Okay, and as I already mentioned, the test is basically nothing but DF test. DF test we will do. So let us see how we can do DF test in R. So in case of R, to do the DF test, you have to basically use a library. The library is T series, the time series T series library, and it is not only DF test. Many things with respect to time series you can do with the T series package. Okay, T series library or T series package. So this DF test, this one is the DF test. It is basically little bit modification of the DF test. It is called the adjusted DF test. So this adjusted DF test for some time series we can do using this command, that DF adf.test, and then you have to give the time series here. Our transform time series is T air passenger. So I provide this time series here. I have to mention what is the alternative hypothesis because I have already mentioned that the alternative hypothesis can be anything that depends on what I want to test. So in this case, I want to test whether the time series is a stationary one or a non-stationary one. So the alternative hypothesis I have to specify, it is a stationary one, that is my alternative hypothesis. And then K, which is basically lag, that you have to provide, and for our case, we will take lag equals to 0. Okay, that is a standard one. Okay, this is a standard one, so I am not going into much about this K. Okay, so let us just do this one and test this, run this command, run these two things. That first import the library and then run the command and see what we get. After running the command, we get this is the result. Okay, we get this is the result. What does this say? This says that augmented DF test we have done. Data, which data we have used? It is basically T air passengers data we have used. The test statistics is minus 9.6003. Lag order we have taken 0. This is the lag order. And the p-value turns out to be 0.01. And just to see the winding also, winding basically see that actual p-value is the smaller than the p-value printed. Okay, so p-value actually smaller than this p-value. So that means at the level 0.01, we actually we reject or accept the null hypothesis. P-value is small, that means somebody, you have already, you must have known this thing. You know or not? If you do not know, I can explain.
Reject the null hypothesis.
Right. So all of you know this one, right? If p-value is small, that basically means we reject the null hypothesis.
So here
so
the
of course
series is stationary.
Sorry?
Sir, it means the series is stationary.
It means the series is stationary because the alternative hypothesis was stationary. Alternative hypothesis was that the time series is stationary. Okay, so it says that the time series is stationary, and that actually we have actually verified using both the things with the visual inspection as well as the augmented DF test. A caution I should mention here. See what I have done here. Instead of taking the transform one, now let us do it on the original data. And from the graph, it is very, very clear that the original data is not stationary. It is clearly increasing pattern is there. Okay. So now if I do this test now over the original data, you see that p-value again is small. It is again saying that the p-value is smaller than 0.01. So that's why I am saying it that, well, only that doing tests like this may give you some wrong information. And we should do both the things together. We should do the visual inspection as well as we should do the statistical test. Okay. So that's why I put it as a caution here, that be caution. It is not that only do the statistical test and you do your analysis. And if we do like this, in this case, we will do something wrong. Okay. So all such exploration is needed. The visual exploration is needed as well as the statistical exploration is also needed. Okay, this point I hope is fine with everyone. Now, this is about the exploration. Now, after that, we will go for modeling. But before that, again, go back to the slide. Okay, again, any question you can ask. Okay, this important, obviously, of course, I hope you have understand that important inference. I have already talked about those things that well. That increasing trend is there, one point. The next point is that there is a seasonality. That means in the July, August, I have peak, whereas near February, January, February, December, I have a drift. And this point is an important one here. In this case, I have a seasonal pattern inside a year, cycle inside a year. That's why basically I have a strong seasonal pattern here. This is clear actually from the plot. Okay, these are basically the inferences. And then, of course, we have also seen the stationary. How can we make it stationary? And here I have basically point out why we need this kind of exploration. And that is actually we have discussed with the data also. Okay. So this is basically the exploration part. Now I will start that modeling part. Before that, again, I ask the same question. Is there any question?
I have one basic doubt. If we
Yes,
are able
go
to
ahead.
predict with the linear regression, then why we are going with this process?
This model you are talking about.
Yes, yes, because we are can directly
Right,
fit the
right.
data.
See, right. Your question is valid question. See, again, I go back to that one. See, yes. So, how can you predict this date? With linear model, you can predict this part. How can you predict it? Of course, you can do one thing. You can think this one as error. You can think this one as error. You can do the linear. You use the linear model and you can do the prediction. But if I can improve this one, if I can predict this jet properly here with some model, then I can combine everything together. I can combine that model for jet here along with the linear model. I can combine everything and maybe that will give much better prediction. Okay? Answer to is
Okay,
your
sir.
first question answered?
Yes, sir.
And
And
that's
here's
why.
the
That's why. Yeah.
another
Yeah. Go
question
ahead.
and how to bring the seasonality into account here also. Like we
Right.
have taken the trend. Yeah.
Right. We have till now we have some seasonality. Of course, we have still now some seasonality is there. Also, maybe there are some pattern. As I proceed, we will discuss. Maybe some other pattern we can find out. Okay. And one of the thing I can actually tell here very easily. See, in this case, if you go to the box plot or in this thing, see that I have peak in February, then peak in July, then August is also closed. So maybe the July value may estimate the August value. Okay. So that is also true even if you go to the stationary data. See, these peaks are basically July values, and then closely after that I have another in most of the cases. Okay. So that means maybe previous value has some effect in the current value. So those things we will basically discuss in the time series modeling. As I have mentioned, I have now talking about the modeling of the stationary one. Of course, there are some seasonalities, some other pattern are there that we try to capture, and then we have to go back. Like we, as I have already mentioned, that okay, maybe that linear trend. In this case, I have a clear linear trend. The linear trend is basically maybe I can use the regression, and that A hat B hat I got, and then once I predict Z here, this A hat B hat can be used, and then basically I can have Y, estimate of Y, which is basically prediction of Y. That will be something maybe here, some estimate here, and then I go back and I take e to the power of that previous Y, e to the power Y 200 to get maybe xt, which is somewhere here, x200, x200, yeah. Okay, clear? So that's why basically all the steps are important. That regression is important. Of course, I can take the things as I mentioned here. I can take this time series as a error. Of course, if I take this one as error, only doing regression is fine. Regression and log, taking the log is fine. But maybe I can do much better thing, and my forecast will be much better. That's why some more models we will explore. Okay, hope that questions are answered, and if any more doubt, you can ask. Okay, I hope there are no more questions. So let us just go with the these models now. So what I am going to do is that I am going to first talk about especially 3 models, and first 2 of them are basically kind of a pure model, and then the next 2 is some combination of this pure model. Okay, so the first pure model is called autoregressive model. So the autoregressive model as its simplest form is given by this. Okay, keep in mind, I am assuming that now I have a time series HT, which I have transformed everything we have done, and we have a basically a stationary time series. Okay, and that one I try to basically now model using some model, I basically used to some model. And this autoregressive model is basically given, the simplest form is given in this particular form, where if you see, this is again a regression model, but there is a basic difference with regression model. In regression model, generally what we take, we take maybe y equals to a plus bx plus some error. And this x is generally the regressor or predictor or independent variable, whereas y is basically the dependent variable. But in this case, you see that when I have a time series x1, maybe x2, x3, x4, and so on and so forth, to estimate x2, I am using x1. So I use x1 to estimate x2. Then I use x3, I use x2 to estimate x3. And similarly, I use x3 to estimate x4. So this way I am proceeding. So to estimate xt, I am using xt minus 1. And the rest of the part is kind of a time series model. Only thing is that maybe this, I can actually include that, or maybe when I make it stationary with mean 0, that I can also explain. I can have some constant here, theta plus. Okay, so it is a kind of this model, this regression model, but here xt is regressed on xt minus 1, and that's why this name is given here, the autoregressive model. Okay, it is an autoregression; it's regressed on itself. Okay, so this is the simplest form of the autoregressive model, but we can easily generalize it. Why only lag 1, xt minus 1? Maybe I have some lag up to p, and I can take alpha 1 xt minus 1 plus alpha 2 xt minus 2, so on and so forth, and alpha p xt minus p plus some error. Okay, this way I can take, and this is generally called the autoregressive model of order p, or autoregressive model of lag p, and the notation we are going to use, it is this notation ARP. Okay. Now little bit talk about in what type of things actually give rise to autoregressive. Sorry, it is the other one, autoregressive model. Okay, what kind of time series actually give rise to autoregressive model? Any question? Anybody told anything? No. Okay, fine. So think about this. Think about the GDP of India or GDP of any country. Okay, you know what is GDP? GDP is the gross domestic product. So it's basically a measure of how much the country is spending on its establishment, its services, everything. Okay. So now you say that the GDP of this year going to depend on the GDP of the previous year. What is the reason? What is the hypothesis here? The hypothesis here is that GDP actually used to, in the previous year, the GDP was used to establish factories, establish manufacturing units, establish maybe industries, establish maybe services, and that actually improves the conditions of the country. Now, in the current year, GDP going to depend on what we have, what infrastructure we have already have from the previous year, plus something which what we have basically purchased or what we have basically installed this year. So clearly, GDP of the current year going to depend on the GDP of the previous year. So for that kind of time series, clearly that autoregressive time series is an important, will have an important role to play. Yes? So is it the example fine? So now you see what is the role of this alpha. The role of this alpha, you can think in this way, the last year GDP, a fraction of last year GDP is used for infrastructure development, a fraction of it may be used for services. Now, the services does not have much effect in the next year GDP, the current year GDP. Okay, the services has not much effect on the current year GDP, but the fraction used for infrastructure development have effect in the current year GDP. That's why this fraction alpha actually takes care of this part. Okay, so this is basically the idea. Of course, if I take alpha equals to 1, that basically say that, well, complete GDP has effect here, but if I take some alpha less than 1 or maybe less than lies between -1 to +1, that basically says that some fraction of the previous year GDP will have effect in the current year GDP. Okay, that's why basically this way we can interpret this coefficient alpha. Okay, so this is basically the idea, and similarly for the lag P, where P is greater than 1, this is nothing but the fraction of T minus 2 years GDP contribution to the current year GDP. Okay, so these are basically the AR model, and this is basically the time series. This kind of time series we can easily use in AR model. So keep in mind, again, I just put it here that Polash also told it at the very end, that whenever we are going to do some modeling, I should have some idea about the background from where the data is coming, through which process the data is generating. Okay, that idea is crucial. For example, for the GDP, maybe this hypothesis is fine, that a fraction of the previous year GDP has effect in the next year GDP. But some other kind of time series, this may not be true. Okay, so this background knowledge is a very, very important thing. Let us move on. Go to the next model, which is called moving average model. Again, in the simplest form of the moving average model is given by this. Here, see that in the case of autoregression model, I have basically that xt is written as some fraction of the previous year plus error, and in this case, basically this is not the case, but the xt is written as some combination of the errors. It is the previous year error, some fraction of that plus the current year error. Okay. That is basically given here. Okay, one point I forgot to mention about the regression, about autoregressive model. This is basically this point, this inertia property of the AR model. What does this mean? This basically mean that suppose if I give a shock to a AR model, that basically means that suppose in some time that some external force come into the play and that I have a sudden jump in the time. Then because this is going to depend on the previous year, now it will decrease slowly and it has an inertia. That is basically called the inertia property of AR model. Because the previous year have an effect. So if in this case I am taking about suppose alpha is greater than 0. So if alpha is greater than 0, it will gradually decrease. It's not that it will suddenly decrease. Because when it has a sudden jump, after that this jump have effect on this point has effect on the next point. So it may decrease, but it will decrease slowly. Then it may have another point which will not suddenly decrease. So it will take some time to decrease and stabilize once again. And this shock actually, of course, not coming from the model, maybe coming from some external force. Some natural calamities or some natural things may come into the picture. Like this pandemic has a huge effect on GDP. Okay, of course, this is not the positive effect, but the negative effect in that case. Okay, now when we go for this model, now let us talk about one example when this model is useful. Let us think of this scenario. Suppose you are selling some bags. Okay, you are manufacturing some bags and you are selling them, and your bag is a very standard one which is available in the market. So if it is available in the market in several shops, then the sale amount will be very less in my shop also. So because it is available in many shops, many places. So suppose for a long time, for several days, I am not able to sell any bag, any of that kind of bag. So after few days, so initially the things are basically zero. Okay, the sale is basically zero. Then at this point, I thought that, well, I am not earning anything from from my bag, why not I try something else? Why not I change my or twist my bag little bit, the design of the bag little bit, and I do that. And when I do that, that bag is not available in any of the market, any of the other shops in the market. So clearly there will be most likely there will be a demand of my bag. So suddenly demand jumps. Because suddenly demand jumps. Now, suppose I produce 100 bags. And because demand jumps and because there is a lot of demand, suppose the demand is 150 bags. So what will happen? I actually sell all the bags and there are 50 customers who go back home empty-handed. Okay? So when I go for next day, so these 50 customers, which are basically do not get any bag, these are basically kind of error at this time point. When I go for the next time point here, what will happen? Maybe some fraction of these 50 customers come back. So this is basically this contribution. Some fraction of these 50 customers may come back to my shop and buy this one, along with maybe some error term added to that. So the demand maybe depends on this beta. Demand may actually fall very quickly or maybe remain little higher. What fraction actually come back depending on that. Okay, but in case of because in this case this extra depends on error. So like the AR model, the effect will not be very long lasting. It will diminish quite quickly. May not diminish in just one step, but in few steps it will diminish. Okay, because it's completely depend on error and also the fact that maybe with time the demand also reduces. That O factor of the bag may be reduced. Okay. So in such scenarios, this moving average model, MA model, is a useful model. And as I mentioned, as we did in the previous case, here also we can talk about general moving average model. In this case, we have taken lag up to Q. So I have beta 1 epsilon t plus beta 1 epsilon t minus 1 plus beta 2 epsilon t minus 2, so on and so forth. Beta q epsilon t minus q, where I have betas at the coefficient and epsilon t's at the errors. And notations we are going to use this one. Okay, notations we are going to use this one, which is basically MAQ process. As before, Q is called order of the MA process or the lag of the MA process. Order is basically more popular terminology here. Okay, now let us see some combination of this model, which is called the AR-MA model. So first, this AR stands for autoregressive, this MA stands for moving average. And this P is basically the order of autoregressive part and Q is basically the order of the MA part. And now you can easily understood what this model is going to be. This model is nothing but the combination of both the models. This is the autoregressive part model, ARP model, and this part corresponds to the AMA model, MAQ model. Okay. Now clearly, in this case, if I take AR, MA, 0Q, that is same as MAQ. Similarly, if I take AR, MA, PQ, P0, that is equivalent to ARP. So that means basically this MAP, ARP and MAQ, these two processes are some special case of ARMA process, Arima process, and this is more generalization of that. And the idea is that maybe I can have both kind of effect may be present, that the current value may depend on the previous values and previous errors. So why not I just combine both of them and see those things. And as I mentioned, if there is no effect of the AR part, that order, I can take the order P equals to 0, and it will basically reduce to MA process, MA process. And if there is no effect of the error, only the autoregressive part is there, I will take that Q equals to 0. So this is kind of a generalization. And as we see that in R, basically we are going to talk about only AR-MA process, because after fitting the data, if I see that P or Q is 0, that actually tells that, well, this is basically a special case of that. Next model is Arima model. So again, this part autoregressive, this part MA. I have a new thing here, which is basically stand for integrated. What is this? This is nothing but a time series xt is called Arima PQ if yt is Arima PQ. Okay, xt is Arima PDQ if if yt is Arima PQ. What is yt? Yt is nothing but the difference, and this is a standard notation for difference, nabla D. That basically means that, well, I am taking the difference of order D. Okay. So as I mentioned in the previous case, in our example, we have taken the difference here. So this is basically the D equals to 1, taking D equals to 1, that the time series we got. So basically, if we see that this time series follows a Arima sum PQ model, then this time series taking difference, before taking the difference, this time series follows a ARIMA P1Q process. Okay, so it actually tells that it is basically useful to do the non-stationarity in the data. So we actually incorporate some non-stationarity into the data, but of course the stabilization of the variance is important before doing that. Okay, so the Arima is basically up to Arima we have only stationarity, but by introducing this I integrated part, this differentiation part, basically we actually incorporated the non-stationarity in the model also. And you see that why it is called integrated, the reason is basically nothing but the differentiated time series follows Arima. So when I go back that, I mean, inverse of the differentiation is integration. So that from there, this integrated term actually comes. So original data, when I have to go back to the original data, I have to integrate it, and integration basically that's why that I is actually incorporated here. So these are some 3 models here. These are 3 models here. 4 models here, and in the linear time series modeling, these are very, very important models. And as I mentioned, when we go for R, we fit a Arima model to the stationary data, and then actually we go back to the original time series for the forecasting purpose. Okay, any questions here? Okay, now let us see 2 very important tools to decide which model to fit. Okay, to decide which model to fit. So these 2 important tools, one is called autocorrelation function, and another is called partial autocorrelation function. Okay, one is autocorrelation function and another is called partial autocorrelation function. So let us go back to this autocorrelation function, which in short ACF. So what is autocorrelation function? Autocorrelation function is nothing but correlation coefficient between xt1 and xt2. So gamma t1 t2 is basically correlation between xt1 and xt2. Okay, and auto, you can understand why auto, the word auto comes here. The reason is basically nothing but it is inside the time series I am seeing the correlation. It's not that I have 2 data, one in y, one in x, and I see the correlation between x and 1. It's not like that. I have just only one time series xt and inside that one time series xt, I take different lag values and I see the correlation. So the idea is basically this. Suppose I take that lag to be 1. So from one time series, I can now make a bivariate data like this, that I have x1, x2, x3, this, so on, so So the idea actually coming from this one. So MA1 is given by this. Now you see that in case of MA1, if I talk about xt, which is basically epsilon t plus beta epsilon t minus 1, and xt plus 2, which will be of the form epsilon t plus 2 plus beta epsilon t plus 1. Now you see that because the errors are generally independent, so there is no relation between this and this. So clearly, these two are basically going to be independent. Okay, these two are going to be independent. So that says that if I try to find out the autocorrelation of lag2 in case of the MA1 process, the autocorrelation of lag2 should be 0 for MA1 process. Similarly, if I go for autocorrelation of lag3, that is also 0, because 3 again I will go later, there will be no relationship between these. So this basically tells that for a MA process, autocorrelation cuts off at the lag q. So in case of lag 1, only at the point 1, I have some positive value. After that, all the positive or negative value, whatever something will be there. After that, all values, theoretical values should be 0. Of course, the practical value may be a little different, but the theoretical value should be 0. And that gives a guideline to us. What guidelines? That if I have a data, if I can plot the autocorrelation function, and if I say that the autocorrelation function cuts off after some lag, that means the data going to follow, data can be modeled with a MA process and the lag also can be found, or the order of the MA process can be found from the cutoff point. Okay, so that's why this auto correlation function is quite important. And if you see the autocorrelation function of AR process has a long-lasting effect. That is also seen from this expression. What I have done basically, xt can be given in this form. Now xt minus 1 can be given as alpha xt minus 2 plus epsilon t minus 1. So if I plug in this value here, actually you get this particular expression. So this clearly says that xt and xt minus 2 are dependent. Now I can even go again further. It turns out x cube, xt minus 3 plus something will be there. So again, xt and xt minus 3, they are also related, or they are also correlated. So that tells us that for ARQ process, the autocorrelation function will not cut off. It will generally decay gradually. If you see the autocorrelation of large lag, it will be very close to 0, but it's not like that it goes to 0 very quickly. It gradually goes to 0. Okay? So from the ACF, I can have some idea. If I plot ACF, I can have some idea that whether the AR is a better model or MA is a better model from the data. Now, for MA model, because MA model is mixture of both the things. In the MA model, I have this AR part, the behavior of ACF look like the behavior of AR model. So it decreases gradually. Okay, decreases is not a right word here. Better to say decay gradually. It may grow from the negative side. It may go towards 0 from the positive side, or it may change the sign. So now come to the partial autocorrelation. So do you have any idea about partial correlation? Somebody please answer.
No, sir.
Okay. So the partial correlation, let us just put it in words.
When the impact of some variable or some lag is reduced.
Right. Basically, partial correlation here, briefly let me tell. See, in the case of the autocorrelation, what I am doing, maybe I have x, let me write x4, x5, x6, x7. Okay. In case of autocorrelation, what I am doing, I maybe try to find out what is the correlation between these and these. Okay, left two correlations. Now, when I am doing this, I am not taking care of the effect of x2, because x2 may affect on x1, x2 may affect on x3. So when I am trying to find out the autocorrelation between x1 and x3, I am not talking about what effect x2 has on x1 and x2. This partial correlation actually takes care of that. Suppose I am talking about the partial correlation between x1 and x3, then the partial correlation between x1 and x3 is a correlation, but that correlation is computed after removing the effect of x2 on x1 and x3. Okay, so partial correlation for a stationary time series, which is log A, the PCF of log K. Yeah. So this autocorrelation between xt and xt plus k with the linear dependence on xt plus 1 through xt t plus k minus 1. Okay. So between xt and xt plus k, I have data point. I have the point xt plus 1 through xt plus k minus 1. I have to remove the effect of these points, these variables on xt as well as xt plus 1. Whatever remains there, I find out the correlation between these the remaining parts. And that is basically the partial autocorrelation. Okay. So that partial autocorrelation, again, R will do the computation for me. I do not need to see exact formulation, but keep the basic intuition behind autocorrelation in mind. Now, the interesting thing is basically this part. Well, this part I have given in table form here. So let us discuss it from here. Interesting part is here. For a regression, autoregressive model of order P, the PACF actually starts off at the point P. For these two, this is decreases. Again, decreases is not a correct one, all will be decay. Okay, all of them decay. So now from the table, some interesting things are there. For ARP model, ACF decays, PCF cutoff. For ARP model, MAP model, AF cuts off, but PCF decays. So they are actually just the opposite behavior. So if I plot ACF as well as PACF, I have some idea whether I should go for AR model or whether I should go for MA model or whether I should go for the general model ARMA model, Arima model. Okay, that's why these two tools, that ACF, that auto correlation function, and partial autocorrelation function, these two tools are very, very important for model selection purpose in case of time series modeling. Okay, so this is one of the way to model. This is the starting point. Of course, after that, as Paulash mentioned in his talk, that we will talk about AIC, BIC, those kind of things also. As we proceed, we will discuss it. Okay, so I hope that ACF, the use of the ACF and PACF are fine with everyone. Okay.
Sir, how to calculate this PACF?
Yeah, the calculation, the numerical calculation has some formula because, but this formula I am not going to give you. The basic idea is basically nothing but, as I mentioned, you just fit the linear model for xt on xt plus 1 to xt plus k minus 1. Fit linear model of xt plus k for xt plus k on.
So please explain by the example, sir, like x1, x2, x3.
Okay, right, fine. So in this case, x1, I fit a linear model, maybe I call some other thing. A1, x2 plus A2 plus some error but you forgot about. This model, I fit x3 equals to some B1, x2 plus B2. This model I fit. After fitting, I can calculate x1 minus estimated value of x1 from this model. Similarly, x3 minus estimated value of x3 from this model. Now, find out the correlation between these two things. This is basically the partial autocorrelation. That's why I'm not giving the exact formula, because exact formula is a quite complicated one. But
yes, it is. The concept is clear. Yeah.
Concept is clear, right? Yeah, but the nice thing is that R will do all things for us. Okay, nice thing is that R will do all these things for us. So now let us see some things in R with that data. So finally, what I have this data. Just let me run this one once again, because I don't know whether anything is changed or not. So now let us see the ACF for this data. So when I run this ACF command here, it gives the plot. Okay, and similarly, when I run the PCF, it gives the plot for the PCF. Now let us try to interpret it. See what happens here. See that the scaling of the lag is some fraction there. So don't worry about that. Just this is the lag 0, this is the lag 1, lag 2, lag 3, lag 4. In this way it is going. Okay. Similarly for PC, this partial one also the same thing happens, that some fractions are given there, but don't worry. This is the lag 1, lag 2, lag 0, lag 1, lag 2, lag 4. That's this way this will go. So first try to see ACF. So what is this? See, lag 0 ACF we always will be 1, because it is the correlation between xt and xt. So correlation with myself will be always 1. So this is always 1 at lag 0. So that does not give us much information in this case. Now These two blue line actually gives us some bound. If the value of the autocorrelation function inside this bound, we'll assume this to be 0. If it is outside the bound, we'll assume this is non-zero. Now, in this case, what happens that lag 1 has some positive value. After that, two consecutive values I can take 0 because this is inside the bound. Of course, after that, this is 1, 2, 3, 4. Fourth one is again some negative value, but I do not care about that much about those things because after one positive, I have 2 0 values. And because I have already told that, see, when I do something in practice, these are basically getting from that data. So they will not be exactly matching with theoretical thing. Theoretical thing says that, well, if I have a MA Q process, then after Q lag, it will be all 0, identically 0. But that will not happen in practice. So in practice, what we do, well, I have some positive here. And after that, I have consecutive at least 2 or so 0. That means we will assume, well, this one is positive. After that, all are 0. Even I have a quite big here, but the lag is very, very big here. So those things I am not going to consider. Okay. The same kind of thing actually happens with partial autocorrelation. In this case also, these two blue lines are the bound. Inside that we will take 0. Outside that I am going to take not going to take. In this case, the lag 0 has some positive value. Don't care. I do not care about log lag 0 because this does not going to give me anything. But after that, everything is inside 0. At least consecutive 2 is inside 0. So that means in this case, PSEF has something. ACF says that, well, maybe I can take MA1 process, and PSEF actually at the initial part it is in the bound 0, and that means basically I can take. Basically, this is not going to give me much information. So that actually tells me together, analyzing both the graphs together, it tells that maybe MA1 process is a good process for this. Okay, fine. This inference is okay with everyone. So if I have this inference, then I can go for fitting of the Arima. Note that in the R, the command is Arima, so everything will be taken care of that. What I did is that I did this one. See, I have not taken the differentiation here. Now I have not taken the differentiation here. My original data, this T data has, first we have taken log, then we have taken differentiation. But when I am doing Arima, because this integrated part is there, I am not taking the differentiation here. What I have done is that I have given the order here. This is the first one corresponding to P, which is basically order of AR process, which is 0. This is corresponding to Q, which is corresponding to the MA process, which is 1, that is basically Q, and the middle one corresponding to D, which is corresponding to the differentiation. So we have to take one differentiation. Once we have to differentiate the data, so 1 I have given here. Then we have seasonal component also. So I have basically given the seasonal component here, and you see what I have done. I have basically you need to give the period of the seasonal component because I have a yearly data. The period is 12. Okay. If I have a quarterly data, period would have been 4, and so on and so forth. Now this one is same as this, but this one you have to give here too, because there are some other options can be given here, but for our case, the same quantity is given here. Okay. Now let us just run this command. Let us just run this command and see what we get. Okay, sorry, fit Arima 1. So after analyzing this one, that results are stored in fit Arima 1, and now I have just printed this one here. The printout comes here. So what is tells? Well, we have tried to fit this model. Model is already we have provided. Then it gives us the estimate. What is the estimate? What is this one? This one is the estimate of, if you see that MA model I have. So MA model, I have this beta 1 because we have that lag 1, only beta 1 is there. So this beta 1 value is this. And then I have the standard error of this estimate is given here. And what is this? This is because there is a seasonality in the data. So it actually fits something called seasonal Arima model to this one, and that is specified by this. So it also gives the parameter estimate for the seasonal part. So seasonal part, Arima model, the MA model, lag 1 MA model, basically beta estimate is this along with the standard error. Now you see that the next line gives us some more information. Forget about this likelihood function and likelihood function because this we are not going to cover in this particular talk. But the other thing we can easily interpret, that one is AIC, as Paula already mentioned. AIC is something which is actually used to compare different models. So, and if you have small value of AIC, that is better. That a model having small value of AIC is better. So that way actually we can see this, and we see that some AIC value is given, and I can use the AIC in a different way. See, these orders we have basically formulated from very empirically from this plot. Now, a natural question is that did I take the correct order? And the answer is that maybe I have taken the wrong order. So, better way to do some order along very close to this may be tried. This differentiation maybe I will not change, but maybe I take 1 here, 0 here, takes 1 and 1 both, maybe 2, 1, maybe 0, 1, 2. Those some combination I should take. And when I should take those things, I should look for this AIC value. And the choice of order that I should take, which corresponding to the lowest AIC value. Okay. With that, I stop here. And in the next lecture, actually, I start from here. Few parts are left here because I am already completed the time. Few parts are there. I will basically discuss those things in the very first part of the next lecture. That will be tomorrow. And then I will go to the some nonlinear models in time series. With that, I stop. And if there is any question, you can ask. I will try to answer. Or any feedback you have, you can tell if there is any part which I can changing of the talk maybe help you. You can tell me. In the next talk, I will incorporate those things.
No, so you're going great, sir.
Okay. Any question? Okay. If not, over to Professor Shairam.
Yeah. So thank you, Ayan. Thanks a lot.
Okay, Ashok, one question. If I want to share the slides and this thing, what I should do? I send those things to you?
Or give it to me. I'll share it.
Okay, sure. I'll do that.
And for today's hands-on session, I've shared the files with you. I've shared it on email as well as on WhatsApp. So please keep those files ready for the hands-on session. Palash will take the hands-on session. And I'll keep this meeting link open so that now we'll break for lunch and then we'll join back at 2. But this meeting link will be open. So you can leave the meeting and join back again, or you can join the meeting if you have a lot of data, if data is not an issue for you. So we'll break for lunch now. And thanks, Ayan. Thanks a lot for...
Yeah, thank you. Thank you, everybody, for listening. Thank you, Ashok, for giving this opportunity. Okay, see you tomorrow.
Okay.
Bye.